and my son also will do. This is after seeing cartoons. My son also. If you score anything, come in now. Then if you this, then if you do other thing mix, and then he will do like this. Then the sound. After seeing all these cartoons. Then he will do like this, and then he will do everything. Song like
once check YouTube, huh? YouTube. This one.
why is the
26 months one time YouTube streaming. स्पीकर का जो है ना
Good morning, everyone. A warm welcome to 3-day faculty development program on research trends in VLSI, communications and signal processing during the period July 8 to July 10, 2021. Firstly, I thank God Almighty for making this opportunity of conducting this program, and also I especially thank for our management to provide these required facilities and throughout the conduction of this event. I also thank our HOD Gauri Madam for their constant support throughout the event. And finally, I thank all the teaching and non-teaching faculty for their constant cooperation and support throughout the event. Coming to today's speaker, Dr. Vinit Paliyamal sir, working as Assistant Professor at Amrita University, Coimbatore. Good morning, sir. It gives me immense pleasure to invite Dr. Vinit Paliyamal sir, working as Assistant Professor at Amrita Vishwavidyapeetham, Coimbatore, to share his knowledge on performance analysis of optical wireless communication systems. He received his BTech degree in ECE from NIT Calicut, Kerala, and MTech degree in communication systems from NIT Tiruchi. He received his PhD degree from NIT Tiruchi with a specialization in free space optical communications. His research areas include optical wireless communication, free space optical communication, and wireless communications. He has several publications in various international conferences and reputed journals, both national and international wide. Now I request Vinith sir to take over the session. Sir, please.
Yeah. Can you hear me?
Yes, sir. Clearly audible,
Yeah.
sir.
Yeah. So, warm welcome to you all and good morning to you all. So, I will share my presentation. So, please tell me if you can see that. So, can you see the presentation?
Yes, sir. Visible, sir.
Yes. Okay, maybe I will turn my video on for a while and after I can switch off. Okay, so myself is Dr. Vinith Palliambil. So I'm an assistant professor in the Department of Electronics and Communication Engineering in Amrita Vishwavidyapitham, Coimbatore campus. So today I would like to talk about the topic of performance analysis of optical wireless communication systems. Okay, so before beginning the section, let me switch off the video. Okay. So I hope you can, all of you can see the presentation in the full screen mode. Is it?
Yes, sir. Yes, sir.
Yeah.
Clear. You can
Okay.
continue.
Yeah. Okay. Thank you so much. So let us firstly go through the contents for today's presentation. Firstly, I will give an introduction about the optical wireless communication technology, the different types, the history, as well as the applications of optical wireless communication systems. And we can abbreviate optical wireless communication as OWC. So hereafter, I will be referring to this technology as OWC. Then we will see the objectives for this presentation. We will see the system model. So basically, the OWC can be divided into two major technologies. Firstly, the optical wireless communication in the indoor, that means inside the buildings. So that technology is called as VLC, or else visible light communication system. Now we also have optical wireless communication for the outdoor environments, and that is called as free space optical communication systems, or FSO. So my emphasis will be more on this technology of FSO. So because that is also my area of my PhD thesis. So therefore, thirdly, we'll be talking about the system model. We'll be looking at an FSO system model. After that, we'll see the channel model, the outdoor optical wireless communication channel model, called as the FSO channel model. Then we do the performance analysis of FSO communication systems. Then we will see how we can improve the performance of FSO communication system using spatial diversity, or as MIMO technology. Then we will see the cooperative FSO communication systems. And after that, we will wind up with a summary as well as discussions on the future scope of this area. Okay. So, coming to the introduction, we know that wireless communication is a very important technology in the lives of almost all the people throughout the world. So therefore, it's a very very important technology that is used by the people on a day-to-day basis. Now, the most prevalent technology that is used to implement the wireless communication is the radio frequency, or as RF-based systems. Now, the drawback of this technology or this RF-based systems is that they are based upon the frequency spectrum, which is licensed. And also, they are in the lower frequency range of the electromagnetic spectrum. So therefore, we know that the bandwidth that is required for a communication is directly proportional to the frequency of operation. So that is why we are going for modulation, so that we can have higher bandwidth, and we are modulating the signal with a higher frequency so that we can have higher bandwidth. So compared to optical signals, these radio frequency signals are in the lower spectrum, or else low frequency band of the spectrum. So therefore, the bandwidth that is possible with this technology is rather limited. And also, we are already spectrum deficit in the case of RF technology. So in the last 5 years itself, we already went spectrum deficit in the RF technology. That means we don't have the necessary spectrum to meet the wireless requirements of the modern day life. So that is why in the 5G and all, we are going for the higher spectrums like millimeter wave technology, etc. So now, so therefore, this will clearly state that there is a high necessity for higher order frequencies. So that is where the optical wireless communication comes into picture. So we know that the optical wireless communication systems are based upon the optical frequencies. So they are in the higher frequency range in the electromagnetic spectrum. So therefore, proportionally, they can support high bandwidth. Okay. Therefore, let us come to this topic of optical wireless communication. So essentially, as mentioned, it is based upon the optical signals. So essentially, OWC is nothing but it is a wireless transmission of optical signals over an unguided medium or else free space between the transmitter and the receiver. Now, we can use different bands, different optical bands. So they can be either the infrared, and they can be the visible light, and they can be the ultraviolet light. So the ultraviolet radiation, all the bands are not used in ultraviolet communication, but only the near band, the near UV band. Otherwise, they are harmful for human body. So as you can see in this picture, the RF frequencies are coming in the lower bands of the electromagnetic radiation. So they have higher wavelength and lower frequency. So as we progress from the RF to IR to visible light to UV to X-ray to gamma, we have higher and higher frequency and lower bandwidth, lower and lower wavelength. And as when we increase the frequency of the carrier, we can have more bandwidth. So that is a rule of thumb. Bandwidth is proportional to the frequency of operation. So now, from this diagram, you can see the RF is between, say, from several megahertz to up to maximum 300 gigahertz. Whereas this optical frequency start, including the IR, starts from the beyond 300 gigahertz to even if you take the case of UV, it can go up to 30 petahertz. So that much high bandwidth we can have. So now, even though the optical wireless technology is not widely used in the modern day life, but even this technology was used in some form or some other premature form in the olden days, in the prehistory. So the first, for example, the first instance of using the optical technologies or else optical communication is the use of the communication using sunlight. So in the olden days, the soldiers, they used to reflect the sunlight to give signals to maybe to warn the enemies or to give signals to other soldiers, etc. So that is also some kind of optical wireless communication. Now, if you look at even some more newer technology, we can see we have devices like heliograph. So it is nothing but the communication of, or else this is a transfer of information by reflecting the sunlight using mirrors. So that is the device that is used for information transfer by reflecting sunlight is called as heliograph. So that is also some kind of what do you say, like primordial or else prehistory or else an older version of optical wireless communication. Now, other kind of optical wireless communication that is used in the history or that was used in the past is communication using fire or land. So we know that in olden days they used beacon fires or fire signals to give say to give some kind of communication. So this is this can be called as a optical wireless communication using fire. So since fire comes in the what you can say in the optical range, so we can tell that is also a type of optical wireless communication. And also we have lighthouses. We have large towers. On top we will have light, say some light. So it is used to give communication to the ships, to give information that how far the seashore is, like that. And also signaling lamps are used for communication between ship to ship. These are also some kind of say optical wireless communication. But the actual modern wireless communication is actually drastically different from this kind of communication. So then the modern communication involves electronic circuitry compared to these kind of mechanical devices. Okay. Now let us look at the major advantages of OWC technology. So the first major advantage, as mentioned, is it is based upon the optical frequencies or optical spectrum. That is in terms of frequency, that is say the frequency is increasing in this forward direction from RF to X-ray. So since they have higher frequency, so they can support larger bandwidth. And also the existing technology, the RF technology is already under a spectrum crunch. So if you look at this, the inset is provided by this RF band, you can see almost all of the spectrum is highly utilized by some or other applications. Therefore, we are already in a spectrum crunch or spectrum deficit in the case of the RF technology. So therefore, it is high time we move to this for implementing wireless communication. Now, one of the major property of the optical signals is that they have very high spatial confinement. So in other words, the optical signals have what you can say like low or a narrow beam width. So therefore, they are not spread throughout the space. So due to that, this spectrum can be used in an unregulated manner. So there is no requirement for buying this spectrum from the spectrum issuing authorities. So therefore, the companies which want to work on this OWC technology, they doesn't have to license this spectrum. So therefore, they can save a premium of money by not spending money on this buying of spectrums. So we already know that in the case of RF technology, so in the options we have seen, these RF spectrums are very costly. So therefore, if we are using this optical wireless communications, we can save a lot of money on the spectrum. So as mentioned, they have very high degree of spatial confinement. So therefore, the reuse factor is very high compared to the RF systems. So the OWC systems will have high reuse factor. And also, since these beams, these optical signals have very narrow bandwidth, narrow beam width. In fact, beam width means that is spreading of the signal in the space. So therefore, that is inherently creating some kind of security. So therefore, we can tell that OWC systems are inherently more secure compared to RF systems. Now, another important advantage is that they have a robustness to electromagnetic interference. So EMI stands for electromagnetic interference. So we already know that in hospitals or in airplanes or spacecraft, etc., we cannot use our RF-enabled systems because they will create electromagnetic interference to the devices that is working in the hospitals or airplanes or spacecrafts. So on the other hand, if you are using optical spectrum, so they will not create any interference to these devices. Therefore, they have some kind of robustness to EMI. So therefore, they can be safely used inside these areas. Or else, you can safely use them in the RF restricted areas. Now, before going further, let us see the major two types of OWC technology. So essentially, any wireless communication system can be used either in an indoor environment or as an outdoor environment. So as mentioned, OWC in the indoor environment is called as visible light communication, and the OWC in the outdoor environment is called as So indoor VLC and outdoor is called as free space optical communication system. So a large portion of our discussion today is about this free space optical communication systems. So you can state like that. So you can put the statement like this. So the indoor OWC technology is called as visible light communication. So the reason for calling it as visible light communication is that basically the signals that is used for this indoor wireless optical wireless communication is the signals in the visible range of electromagnetic spectrum. So it has two advantages. Firstly, it can give very high bandwidth communication. Secondly, these signals can also illuminate inside the building. Therefore, it can be used for both illumination purpose as well as communication purpose. That is why we are using the visible light in the indoor environment, and this technology is called as visible light communication. Now, the outdoor OWC technology is called as free space optical communication systems. So here, the optical signals are transmitted in the free space directly between the transmitter and the receiver. That is why it is called as free space optical communication. So it can be abbreviated as FSO. So hereafter we will try to refer this to as FSO. And also, if we abbreviate FSO communication, then we can call it as FSOC. Now let us compare the performance between the RF and FSO systems. So here you can see a table. So this table contains three columns. The first column we have the feature, the different system feature, the communication system feature. So these features can be either the cost of the system, the spectrum regulation, the capacity of the system, and the security of the system. And in the second column we have the FSOC, or else free space optical communication system technologies. And the third column we have RF systems. Now if you compare these two technologies side by side, firstly let us see the cost. So in terms of the cost, FSOC systems have rather lower cost compared to RF systems. Now, if you look at the spectrum regulations, you can see that, as already mentioned, FSOC systems are using the optical frequencies which are unregulated because they have very high spatial constraint. So there is no need to pay any premium for buying the spectrum. But on the other hand, RF systems are working in the regulated spectrum. Therefore, we have to pay some amount of money, even not some amount, a very large amount of money has to be paid in order to get these, or in order to use this spectrum. Now, looking at the capacity, FSOC systems have the potential to give data rates of the order of 100 to 1000 Mbps on an average. So these are average values. So even even there are devices which can give even more than this capacity. Now, RF systems on an average can give 10 to 100 Mbps. So, in all these three things, clearly FSOC is a winner. Now, in the case of the security feature, as mentioned, since FSOC signals have high spatial confinement, they are difficult to tap. So if eavesdroppers cannot intercept optical signals due to their narrow bandwidth compared to the RF signals, which are somewhat, say, omnidirectional. So therefore, security is rather high in the case of FSOC systems, and security is rather low in the case of RF systems. So therefore, at first look, we can see that FSOC has many advantages compared to the RF systems. But even though this is the fact, but there are some disadvantages for FSOC systems also. First thing is that they need strict line of sight between the transmitter and the receiver. So if any tampering is there between this line of sight, then there is a signal outage at the receiver. So that is one drawback of FSOC system compared to the RF system. Now, another drawback is that FSOC cannot support mobile users as much as that is used by the RF users, or else as much as that is supported by RF systems. So these are the main drawbacks of FSOC systems. So therefore, we cannot tell that FSOC can fully replace RF systems in the case of, especially for providing mobile communication. But FSOC can be used to replace some kind of RF systems, especially in the backhaul region. So the backhaul stands for the communication between the, say, some wireless receiver, say wireless tower, and the wireless base station, and the corresponding the fiber optic backbone. So this connection between this base station and the fiber optic backbone is called as the backhaul. So in these scenarios, FSOC is a rather good option compared to the RF technology. And also FSOC can also be used in the, or else the optical wireless communication can also be used in the indoor scenarios. Okay, so now let us see some applications of FSO as well as some use cases wherein this technology has already been used or else was used in a pilot manner. So generally, FSO can realize metropolitan networks, then wireless backhaul systems, as mentioned, that is connecting between the base station and the fiber optic backbone. And it can be used in military networks. So in the case of the military, the security is one of the most important parameters. Therefore, since FSO has higher security, it can be used in military networks. And also it can be used in satellite communication. So for example, if you take the company like Starlink, so which are trying to provide satellite-based broadband connectivity to the users, especially the remote users. So in those cases, this communication, this connectivity is provided by virtue of what you can call like low Earth orbiting or else LEO satellites. So these satellites are actually some rather say 100 to or else around thousands of kilometers, just of the order of several hundreds of kilometers above the Earth's surface. And these satellites can be interconnected using optical signals. So that is what is FSO in the case of LEO satellite communication. So for all these things, we can use FSO technology. Now, especially in the case of satellite communication, if you use optical signals in the satellite communication, then the speed of the communication will be of the order of the speed of the light. However, what is the speed of the signaling? So therefore, this can be used to provide very low latency communication, say of the order of around 30 to 40 milliseconds. So if you look at the current latency, so we are experiencing of the order of several 100 millisecond latency. So now, if you look at this, if you implement this LEO satellite-based broadband connections using optical signals, then you can provide very low latencies, maybe of the order of 30 to 40 millisecond latency communication. So far, there are many commercial FSO products that has been already developed. So this can support even bandwidth of the order of 100 Mbps to 2.5 Gbps. Now, if you look at some use cases, so in the 2010 Football World Cup conducted in South Africa, so they used this FSO communication technology in order to connect between the temporary media rooms and the football stadiums. Now, another use case is that in 2001, when there was the September 11 terrorist attack happened in USA, in the Pentagon and the World Trade Center. So when these buildings were demolished, the existing wireless or the existing communication infrastructure was damaged. So therefore, there was a need for setting up a temporary communication network, and this was implemented by using FSO technology. So these are the different use cases that has been done in the case of FSO technology. Now let us look at the objectives for today's presentation. Firstly, we will study about the performance of an FSO link. And in this FSO link, we will see what are the effects of the fading faced by the optical signals due to the atmospheric turbulence and the pointing errors. And thirdly, we will see how we can improve the FSO performance, especially by using spatial diversity technology. Thirdly, we will see the performance analysis of a cooperative FSO communication system. So now, before going further, let us firstly look at the system model for FSO communication. So what are the components that are used in FSO? Now, another important advantage of the FSO communication is that since they are using the optical spectrum, so the existing components that are used to deploy the optical fiber technology can also be used in the case of the optical wireless communication systems. So that is another major advantage of the FSO communication system. So therefore, we doesn't have to engineer new devices. Rather, we can use the same devices, or maybe we can modify them and we can use for the FSO communication technology. Now, any system model, any system, if you look at, it will be having a transmitter. So the transmitter, the baseband processing will be happening in the electrical domain. Now, the final signal, which can be marked by this ITX, which will be an electrical current. So that will be used to modulate an optical transmitter. So it can be either a laser diode or else a light emitting diode. Now this signal is transmitted out of the free space and it will be received at the receiver via a photodiode, that is a photodetector. So this photodetector will create a current IRX that is proportional to the ITX. Now the further processing will happen in the electrical domain at the receiver. So this is what is the structure of a basic FSO system. So if you look at each of these components in detail, firstly, there are majorly two components that can be used as a transmitter. That is a LED light emitting diode or else a laser diode or else a LD. Now, generally, LED wider emission width, or else they can emit light in a wider beam width. So therefore, compared to the laser diodes, they can be used, since they have wider emission beams, they can be used in indoors. That is why for VLC technology, we will be mainly using LEDs as a transmitter. And also, in addition to this having a wider beam width, the LEDs also have, the LED power is rather considered to be eye safe. That is why they are used in indoor environment. So therefore, we can have higher powers, emission powers in the case of the LEDs compared to laser diodes or else LEDs. And also, LEDs are more difficult to damage, as well as they are cheaper compared to the LEDs. And also, LEDs have lower sensitivity to temperature variation. That is, as temperature varies, their performance doesn't vary much compared to laser diodes. And also, the driver circuit that is required to drive the LEDs are comparatively simpler compared to the laser diodes. So these are the advantages of LEDs compared to laser diodes. But laser diodes also have many advantages compared to LEDs that will make them a good candidate for the use in the outdoor environments. Actually, they can be modulated at very high speeds compared to LEDs. So therefore, this makes them a very good candidate to provide very high data rate. And also, they have very narrow beam width. Since they have narrow beam width, their energy is not spread out in space when they travel to very longer distances. So therefore, they can be used for very long distance communications. But the problem with LEDs is that LEDs are working based upon the stimulator emission. So therefore, they require rather complex driver circuits compared to the spontaneous emission characteristics of the LEDs. And also, LEDs are more sensitive to temperature variations. So these are about the transmitters. Now come to the case of the optical receivers. Basically, an optical receiver is a device that will take on the optical signals, and when these optical signals are incident on the photodetector first, they will create an electrical signal. Now, therefore, it is always very important to to improve the sensitivity of the detector with respect to the optical signals. So this sensitivity can be represented in terms of responsivity R, and we can represent it like R is equal to QE into small case q into lambda divided by hc. So this is the parameter that will represent this optoelectric conversion in the case of the photodetector. So here this QE is nothing but the quantum efficiency. So that is nothing but how many electron or how many carriers are generated for a given number of photons that is hit on the photodetector. So essentially the idea is that we want to increase the number of carriers generated for a given number of photons that are incident on the photodetector. So that is the quantum efficiency of the photodetector. So we need devices which have higher quantum efficiency. For example, if you look at this formula for a given frequency, you can see that all of these q, lambda, and h and c, all of these are constants. So h is Planck's constant, c is the speed of light, lambda is the wavelength, and q is the charge. So the basic charge in Coulomb, electron charge in Coulomb. So all these things are constant. So therefore, the responsivity is directly proportional to the quantum efficiency of the material used. So therefore, we need materials, or else we have to engineer materials which have high quantum efficiency. Now, the generally two preferred types of detectors are the pin diode, and secondly, we have the avalanche photodiode. So these are the two major detectors that is used at the receiver. So a pin diode is nothing but it's a PN junction diode with an intrinsic semiconductor in between the P and N junctions. So why we are adding this intrinsic semiconductor is that it will increase the quantum efficiency. So as the photons hit, more carriers are generated if you are adding some intrinsic semiconductor in between the P and N junctions. That is what is a PIN diode. Now in the case of the avalanche photodiode, so here the avalanche effect in the case of semiconductor is utilized to create more carriers with respect to the number of photons hit. So generally, if you look at the PIN diodes, they are cheaper compared to the APDs. So APDs are nothing but avalanche photodetectors. So in addition, they also doesn't require that much high bias voltage compared to the APDs. So in the case of the APDs, in order to establish the avalanche effect, we need to bias them under high voltages. So that is not required in the case of PIN diodes, PIN photodiodes. And also they have lower temperature sensitivity compared to APDs. But the sensitivity of the PIN diodes are rather low compared to the APDs. Say they are 10 to 15 dB lesser sensitive compared to APDs. Now on the other hand, APDs have very high sensitivity compared to PIN diodes, but they need to be biased at very high voltage. So this high voltage will induce a high electric field across the avalanche photodiode. So therefore, whenever some photons are hit on this photodetector, it will create some electron-hole pairs. So these pairs will interact with other atoms, and it will create which will result in generation of new electron-hole pairs. And these newly created electron-hole pairs will again bombard with other atoms, and it will even further create more number of electron-hole pairs. So this is called as the avalanche effect. This concept of avalanche effect is utilized in the case of the APDs in order to improve in order to increase the quantum efficiency. So we have already seen that for a given frequency, in order to increase the responsivity of the detector, we have to increase the quantum efficiency. So therefore, this avalanche effect is used in the case of the APDs. Now let us look at the performance analysis of FSO system. So that is what is the major topic of our today's talk. So essentially, an FSO system will be having a transmitter and it will be having a receiver, and the signal will be transported over the free space. Now here, in our discussion, we assume that we are using the polarization or else PLSK modulation. So this is nothing but polarization shift key. Okay, so that is nothing but for if you are transmitting binary information, for bit 1, we will be using some optical polarization, and for bit 0, we will be using another orthogonal or else some other polarization. Therefore, the signals are, what you can say, like modulated as per different optical polarizations. That is what is called as POLSK modulation. Now, if you are transmitting a symbol X from the transmitter across this free space optical channel, then at the receiver will be receiving a symbol Y, which can be modeled as Y is equal to RHX plus N, where R is the responsivity, H is the fading coefficient. Since we have a wireless medium between the transmitter and the receiver, there will be a fading. So that fading is parameterized by this coefficient H. So therefore, the received signal will be RHX plus N, where N is the additive white Gaussian noise. Now, so before going further, let us see what is the reason for this fading coefficient H. Now, if you look at the free space optical channel, this channel actually will contain different this kind of different eddies. So these eddies are having different refractive index. So the reason for these different eddies are that the free space will have, what you can say, like different varying amount of temperature and pressure. So these what you say, eddies with different temperature and pressure, they will have different refractive index. Therefore, what will happen is that whenever the optical signal is transported through this channel, they will suffer different scattering. So that if you're transmitting a single beam, but essentially due to this scattering, the received signal will have three components. Firstly, there will be a scattered and independent component, totally independent component from other components, that is E superscript GS. Then there will be a scattered and coupled component to the line of sight component, LOS component, that is E superscript C S. Then there will be a LOS component. This is nothing but the EL. So this is called as, this kind of fading is called as atmospheric turbulence. Therefore, signal arrived at the receiver will have these three components. In addition to this, there is also a possibility of pointing error. That is nothing but sometimes the signal or else the beam that is transmitted from the transmitter to the receiver may suffer some kind of misalignment, which will result in what is called as pointing error. That is also another kind of random fading phenomenon. Okay, so now therefore optical beam will suffer two kinds of turbulence, two kinds of fading, channel turbulence as well as pointing error, which will result in what is called as the fading coefficient H. Now we can, since these two phenomena are random in nature, therefore we need what is called as PDF or as a probability distribution function in order to characterize this fading coefficient. So generally this is modeled using a Malaga distribution or else M distribution. Now this is the this PDF expression for this fading, for this type of fading. So I'm not going to for the details of this function here, but just you can understand that this is a function that is represented in terms of a major G function, which is a hypergeometric function. Okay, now coming to the performance analysis. So majorly in the case of the wireless systems, we will be interested in performance in terms of either the bit error rate as well as the channel capacity. So the bit error rate is nothing but if you are transmitting some bits, how many bits are properly received at the receiver. So bit error rate will count how many bits are received in error at the receiver. Now before estimating the bit error rate, we have to see what is the signal to noise ratio at the receiver. So this which is abbreviated as SNR. So SNR is nothing but that is equal to the power, the signal power divided by the noise power. Here the signal power is equal to R square into H into PR divided by 2 sigma n square, where sigma n square is the noise power variance. Okay, so now if you look at the the BR expression, as mentioned, we are using the POLSK, the polarization shift keying modulation with the FSO communication. So for a POLSK based communication system, the BR is given by this formula. That is nothing but is equal to the BR can be represented as PEC of H, that is equal to 0.5 into exponential function of minus R square H PR divided by 4 sigma n square. That is nothing but 0.5 into exponential of minus SNR divided by 2. So this is the error function, this is the bit error rate. for a PLSK based FSO system. Now the problem with this expression is that this is a function of h, and h is, we know that it's time varying, it's a random parameter, and therefore it is a time varying function. So therefore, in order to get an average field of this BR, we need to take the the mean of this instant. This can be called as the instantaneous BR. So we can take the mean of the instantaneous BR, which is called as the ABR, or else average BR. Now, generally, statistically, in order to find the mean or else the expected value, we'll be integrating it with the corresponding PDF of the random variable. Here, the random variable is h, so the PDF of the random variable is fh of h. So if we integrate this function with respect to this fh of h, we can get the average BR. And here, the fh of h, the formula for fh of h, we can substitute that, and we can integrate this function, and the corresponding average BR function can be obtained like this, and it is represented in terms of P. Okay, so now let us look at the plots of this BR so that we can get some insights on this BR. These are the plots for this average BR. So here you can see asymptotic. So asymptotic means the BR for high values of SNR. So there we will approximate our BR function for the high values of SNR. So that, therefore, in that way we can we can simplify that BR expression. But anyway, this asymptotic BR will be only accurate in the case of high SNRs, high values of this SNR. So the SNR is running in the x-axis, and average BR is running in the y-axis. So here we are plotting this SNR value for different channel turbulence values. So these channel turbulence are parameterized by the parameter rho. Generally, if the value of rho is less, there will be higher channel turbulence, and if the value of rho is more, then there will be less channel turbulence. Now, looking at these curves, you can see that these blue curves correspond to the non-asymptotic BR curves. So clearly, you can see that as the value of rho increases, turbulence increases, we have more BR, and as the value of rho increases, the channel turbulence decreases, and we have lesser BR. So this is the case of a single input, single output FSO system. So we are assuming only one transmit aperture and only one receive aperture at the in the system model. Now, generally, in the case of a general communication system, we require SNR, we require BR of the order of 10⁻⁻⁶. So now, if you look at this curve, if we want some BR of the order of 10⁻⁶, we need the channel turbulence to be as low as possible, as well as there should be high SNRs. So therefore, if we need a high SNR, we need to use more signal power at the transmitter. So that is one drawback of this SISO FSO system. So if you want a satisfactory value of BER, then we have to increase the SNR. Or else we have to, in turn, we have to increase the signal power. Now this is again the BR plots for different values of pointing error. Pointing error is also inversely proportional to the value of G, which is parameterized by this pointing error, is also inversely, the value of this is inversely proportional to pointing error. If G is more, then pointing error is less, and if G is less, the pointing error is more. So therefore, for low values of pointing error, we have more BER, that is more error of the receiver, and therefore to reduce the BER, we have to reduce the effect of the pointing errors. So another parameter, that is the channel capacity. So the channel capacity expression is for a wireless communication system can be expressed in terms of the channel capacity theorem, which is equal to CFH is equal to log to the base of 2 of 1 plus SNR. So this is this parameter R square H PR divided by 2 sigma square is nothing but the SNR expression. So this will give what is the maximum possible channel capacity for this given communication system. Again, this is a instantaneous instantaneously varying function with respect to the channel fading parameter H. So therefore, we have to find the average value, the mean value, which can be calculated by averaging it over the channel PDF, which will result in this integral expression. We can solve this using like already mathematical identities are available to solve these integrals, and we can get the final corresponding average value of the channel capacity. And this average value of channel capacity is also called as ergodic channel capacity, or else ECC. Okay, so this is the expression, and this is the plot for that. Here we are plotted this for different SNR, different SNR in the x direction, and channel capacity, and the unit of this channel capacity is bits per second per hertz. So this is a normalized channel capacity. We are normalizing it with respect to the bandwidth. So therefore, that is why we are getting the unit bits per second per hertz. Okay, so this is the plot for that. So this is the maximum capacity that we can get for this corresponding system, FSOC system. Okay, so as mentioned in the previous slide, if we want satisfactory performance in the case of the FSO technology, especially single link FSO technology, we need to have very high SNR. But normally, we won't be having that much high power devices. So therefore, we have to reduce the transmitted signal power. So for that, what we can use what is called a spatial diversity. So the spatial diversity is nothing but there is an assumption that in a wireless channel, at any given time, there can be multiple uncorrelated channels. So if one channel is in deep fade, the other channel may not be feeling that much fade. So that is what is the idea of spatial diversity. So in order to accomplish this spatial diversity, we need to have multiple transmitters and multiple receivers. So that is what is called as the MIMO system. So generally, we can have M transmitter. In the case of the optical systems, it is called as aperture. So we can have M transmit apertures, and we can have N receive apertures. So generally, since there are multiple signals coming at the receiver, we need some kind of combined technique at the receiver. So here we will use what is called as maximal ratio combining technique at the receiver, which is called as the MRC technique. Now, in the case of the MIMO system, the symbol transmitted, if X is transmitted, then we will get multiple copies at the receiver. So at any given receive aperture, say in the receive aperture, the signal received can be represented as Yn. So that will be a summation of multiple signals coming from the transmitter. So essentially, there will be a M signals coming from the transmitter. We can sum them over, and we can add with the additive white Gaussian noise. So this will be the corresponding received signal at the nth receive aperture. So here, each of this channel will have its own fading coefficient, which is parameterized by h n comma m. Now, if you assume that the transmitted signal power was Pt, then the SNR can be represented as a summation function like this. So this is for the MRC case, maximum ratio combining. So therefore, the SNR will be equal to gamma bar divided by n, summation of n varying from 1 to n, summation of m varying from 1 to m, h n m the whole square. Here gamma bar is nothing but eta pt whole square divided by m square into sigma square. Again, for this given SNR, we can find out the instantaneous BR. So here we will assume the BPSK modulation. So for a BPSK modulation, the expression for the BR is Q function of root of gamma, where gamma is SNR. Now we can approximate this Q function in terms of this integral function. Now this instantaneous BR, as mentioned, that is a function of the channel coefficient, which is time varying. So we have therefore we have to find out the expected value of this BR. So therefore we can integrate it over the channel PDF. So this integral function can again solved using mathematical. There is already established mathematical identities to solve this integral, and we can get this corresponding BR function. So this is the corresponding BR for the given MIMO system. So here, for simplicity, we are assuming that number of transmit apertures, that is M, is equal to 1. So therefore, this is a CMOS system, single input, multiple output system. Now we can again, to get insights, we can plot this BR expression, and we can see that if you are plotting it for different values of N, that is for a given single transmit aperture, we can increase the number of receive apertures, So as the value of n increases, the spatial diversity, the amount of spatial diversity increases. And also we can clearly see here. So we have plotted here for 3 different scenarios. That is, firstly the seesaw case, single input, single output case. That is only 1 receiver aperture, then 2 receiver apertures and 3 receiver apertures. So if you look at this blue curves, they correspond to, this is a seesaw case. This is n is equal to 2 case. Here is n is equal to 3 case. In the seesaw case, n is equal to 1. As the value of n increases, the bit rate drastically reduces. For example, suppose we want something like 10 raised to minus 6. That is an acceptable thing. So here clearly you can see that if for n equal to 3, we need to transmit only with an SNR of around, say, we need to have only a receiver SNR of around 20 to 24 dB compared to the case of seesaw. In seesaw, even we cannot achieve that even beyond a SNR of 80 dB. That is the advantage that we can get by the MIMO technology. Our third scenario is the cooperative RF FSO communication system. So here we are using like FSO technology along with the RF technology. So if you look at this system, you can see that most of the mobile users, they prefer the RF mode of communication because they will support more mobility, because RF signals are more ubiquitous compared to FSO signals. On the other hand, FSO signals are rather spatially confined. So therefore, the signals that is transmitted at this base station can be transported over a FSO link to the corresponding, say maybe the fiber optic backbone starts from this destination. Therefore, this is the source. This base station can be taken as a relay, and the destination is actually, it will be the actual fiber optic backbone. Now, this relays can be of multiple types. It can be amplify forward, it can be decode and forward, and it can be a combination of that. So it can be many types. There are many types of relays. Essentially, we will be using in this case an AF relay, that is an amplify forward relay. So the signals that are received at this relay will be amplified in the electrical domain, and then they will be transmitted over the FSO link. So this kind of systems are called as asymmetric RF FSO communication systems. Now, here there will be 2 SNRs, gamma 1 and gamma 2. Gamma 1 is SNR in the RF link, and gamma 2 is SNR in the FSO link. Now, we can model this RF channel using this Nakami-M distribution. This is the PDF for this RF channel. And if we integrate this PDF for a given value of SNR, we can get the CDF, that is a cumulative distribution function. So therefore, in this way, we can obtain the CDF. So later on, we will use this CDF. And also, for this Nakami function, this M is a Nakami-M fading parameter, and usually the value of M will be greater than or equal to 1/. As mentioned, FSO channel is modeled using the M distribution, and now we can convert this channel PDF in terms of the SNR from the channel coefficient, and we can use we can express this function in terms of 2 types of receivers. Firstly, the heterodyne detection based receiver, as well as the intensity modulation and direct detection based receiver. So for R equal to 1, we have heterodyne detection. R equal to 2, we have IM bar DD. Now, same is the case of RF system. We can also find the CDF by integrating this PDF from 0 to gamma 2, and we can get the corresponding channel CDF. Okay. So now, if you look at this relay, as mentioned, the relay is AF type, amplify forward type, and also an AF relay is also 2 types, variable fixed gain and the variable gain. So here we assume a fixed gain based AF relay. Now, in the case of a fixed gain based AF relay, the the effective SNR of the destination can be modeled in terms of the SNR in the 2 links, gamma 1 and gamma 2 as gamma is equal to gamma 1 into gamma 2 divided by gamma 2 plus C. Now, we can use this function in order to find the effective CDF for the overall source to destination SNR gamma. So therefore, if you integrate this function, here if you take gamma 1 as, if you take gamma 2 as constant, then gamma 1, then the probability of gamma 1, which is less than gamma into gamma 2 divided by gamma 2 plus c. And if we integrate that over varying values of gamma 2, then we can get the corresponding CDF for the overall SNR. And we can solve this integral and we can get this corresponding final closed form expression for the overall CDF. And later on we will use this for finding the other performance parameters. Now, an important performance parameter in the case of RF systems, in the case of wireless systems, is outage probability. So the outage probability is nothing but the probability of the receiver SNR falling below some threshold. So at the receiver, we need some minimum threshold, and if the receiver SNR is below that threshold, then we cannot detect the signal. So therefore, the probability for that outage is called as outage probability. So this outage probability is nothing but is the probability of the SNR, receiver SNR gamma I less than the threshold gamma. So that is nothing but the CDF, def gamma of gamma. So we already have found out the formula for CDF. We can substitute that, and therefore we can get the outage probability function. Now we can plot this outage probability function, channel turbulence and different values of rho. So here we have plotted it for both the receivers r equal to 1, that is heterodyne detection, and r equal to 2, that is IM bar dt. So you can see that heterodyne detection has better performance, lower outage probability compared to the IM bar dt. So the reason for this is that IM dt uses only one part of the signal, one half of the signal compared to the heterodyne detection. That is why heterodyne detection have better performance. Now similarly, the channel capacity can also be estimated. So here for this computing of the channel capacity, we are modifying this channel capacity theorem in terms of the CDF of the channel, and we can then integrate this function, and we will get the corresponding closed form expression for the channel CD or the channel capacity. And also, if we are plotting this channel capacity, we can get this plot. Again, we can see that R equal to 1 is having higher channel capacity compared to R equal to 2. That means the heterodyne type receiver is better than the IM bar dt receiver. Now let us come to the summary and conclusions. So far from this discussion, we can see that the OWC and the FSO communication technology is a new wireless communication technology, which is using the optical signals to transfer data between the transmitter and the receiver in a wireless manner. So it has many advantages compared to RF, like unregulated spectrum, cost effectiveness, then easy deployment and reconfiguration, etc. But we have seen that for a single input, single output FSO system, the performance is drastically affected by the turbulence-induced fading as well as pointing errors. So therefore, we need some technology like spatial diversity technology in order to improve the performance. And later on, after that, we have seen a cooperative communication system. So the cooperative communication is nothing but a communication involving multiple links, which are aggregated by a relay. So there we have aggregated RF systems with the FSO systems using an amplified forward relay, and we have again calculated the outage probability as well as channel capacity for this RF FSO asymmetric RF FSO system based on AF relay. So these are the summary of the main points or the main ideas that we have discussed so far. Now let us look at what are the future scope available in this area. Now, one important parameter that we have assumed to be negligible in our throughout our discussion is the non-zero Bohr-Site error. So actually, the pointing error will also contain another component called as the non-zero Bohr-Site error. That is nothing but the permanent misalignment between the transmitter and the receiver beams. So this will happen over the time. So for some up to, without losing the generality, we can assume that this permanent misalignment is negligible. So that is what we have done. But in any case, in the case of systems which are deployed for a very longer period of time, they will have some non-zero Bohr-Site error. So we can extend the performance analysis for FSO links containing this non-zero Bohr-Site error also. And also we can employ channel coding methods or else error correction codes in order to improve the performance. So that is also another domain, or else that is another scope for future work. And thirdly, sometimes in the spatial diversity systems, all the links may not be fully uncorrelated. There can be some channel correlation as well. So in these cases also, we can do some performance analysis. So that also can be done in the future. Now, all of these works mostly was fully theoretical and simulation based. So we can, we can practically verify these things by using some experimental setups. That is also another scope for future. And also, this free space technology can also be extended to underwater communication. Optical signals can be used in underwater communication. So the novel journals in this domain are coming, which are extending this FSO technology to underwater communication. And similarly, this FSO technology can also be extended to airborne as well as air-to-ground communications. So these are the scopes for the future work. So Francis, and thank you.
Thank you, sir.
Yeah. So if you have any questions.
Yes, sir.
Yeah.
I request all the participants, if any questions are there, you can directly interact with sir. Sir, we have 2 questions in chat box, sir.
Yeah, let me see that.
Yes.
So I think the first question is, can FSO technology be used for long-haul communication as like optical communication through fiber? So yeah, to answer this question, actually, as mentioned, in the case of the free space, we are having the issue of channel turbulence. So that will induce some kind of fading. So this fading is the prime reason that will limit long distance communication in the case of any wireless technology, either it be RF or either it be FSO. So therefore, in the case of the terrestrial communication, we cannot have that much long haul communication. But if you are using relays in between, then we can extend this to long haul communication. But if you look at the satellite communication, if you look at the outer space communication, as mentioned, there is a Starlink that is by Elon Musk. They are proposing to provide connectivity to, especially the rural people. So in that cases, they are planning to connect between these satellites, which are providing this connectivity to the users. So the interconnection between these satellites are, are planned to be using this optical signals. So therefore, this long-haul communication is possible in the case of outer space, but it is very difficult in the case of the terrestrial communication. So I hope I have answered your question. So can we go to we'll go to the next question. So the question is like, in VLC, will the signal strength depends on the light footage? So maybe I assume that they are asking about the width of the signal. Yeah. As mentioned, in the VLC, we are using the LEDs, so they will have higher beam width. So therefore, any electromagnetic spectrum which have wider beam width, the signal power will correspondingly reduce. So therefore, depending upon this beam width, definitely the signal strength will, if it is more, the signal strength will be less, and if it is, if the beam width is narrow, then the strength will be high. Okay, so if there are further questions, you can ask.
I request participants once again, if any queries are there, you can directly interact with sir.
Dr. Vinith, this is Dr. Raja from IIT Hyderabad. I have a few questions. Hello. How are you?
Yeah, how are you, sir? Yeah.
Okay, thank you.
Yeah.
From your presentation, I found that you mentioned that FSO is has many advantages over RF system.
Yes, sir.
So, with respect to hardware complexity, how it is feasible, whether it is cheaper than RF transceiver or it is costlier?
Yeah, actually, compared to the RF, it is generally on average it is cheaper only, especially if you are using the LED based systems. But if you look at, but if you are using on the other hand laser diode based system, then it is somewhat costlier. But anyway, generally we can tell that the overall cost for a deployment, overall cost for everything, in overall manner, as mentioned in one of my slides, it is rather cheaper only.
Okay. Any specific technology exists based upon that technology they fabricated transceiver, full chip transceiver?
Yes, yes, yes. Some companies like Epsona, they have already started to develop some products, some FSO-based products, as well as FSO as well as VLC-based some products. So basically, all these are mainly for the lab purposes, for experimental setup purposes. So the actual commercial products for the domestic users or for the end users is actually yet to come.
Okay. So as far as RF is concerned, we always depends on the
yes, sir.
EMS, TSMC fabrication fab companies in,
yes, yes,
in Belgium and France. Okay. For MMIC fabrication, we always depends on the EMS foundries in France and US. So similar way, where we approach to fabricate our FSO transceiver chips. Suppose we are developing our own application, we need to fabricate means where we have to approach. Any idea?
I think this Epsona-based companies, some of the companies are there in Germany and even UK also. Okay. Yeah, there are some professors like Harold Haas. They are working. They are actually the pioneers in this VLC technology. So they are basically in Scotland. So they have some setups there. But basically, this you cannot tell it is like so much advanced like the RF-based systems.
Okay.
So yeah, mostly it is like in infancy. So just the technology and the equipments, everything is being what do you say, like in the engineering phase. Such a final in the prototype phase, the final outcome is yet to come.
Yeah, recent trends, we are developing the IoT RF transceiver and the single chip itself, both transmitter receiver, even the antenna also we fabricate on the chip itself. That is
yes. Correct.
So likewise for your optical applications, how the people are integrate both transmitter and receiver on chip, or they put it that some part in the off chip and some part in the on chip? How they are developing the transceiver?
Yes, actually we can develop them in the same chip itself. Actually, because what you can say, like there is like a coherence length. If you look at this, what you can say, like there is a minimum distance that should be there between the beams. So the coherence length is actually less in the case of optical signals. Therefore, we can make it the same chip itself. Even some of the technologies, there are some like inter-chip communication. So even this inter-chip communication using this optical signals are also possible.
Okay.
Yeah, rather than transporting the signals through some wires, so that you can use the light beams to do the inter-chip communication, very high bandwidth communication. So in the case of the digital systems, we know that we require to transport the data in a very high, say for example, the memory to processor communication. If you take that is of the order of very high speed. So those things can be even processed in the optical domain. So there are theoretically all these things are possible, but as far as even if I am concerned, I am not much, but I don't have much knowledge about the practical components that have been, what you can say, like whether it is created or fabricated or not. But theoretically, all these are possible.
Okay. We already submitted one proposal regarding this FSA-based transceiver design only. But due to that, some difficulties in the fabrication side, we didn't get that fund from Government of India. And also, in India, even for RF and MMIC chip also, we always depends upon the foreign countries. There is no facility in India till now.
Yes.
So for MMIC fabrication, we have to spend around 1 crore rupees to fabricate one ICs. So that is why I'm asking how feasible in FSO the people are fabricating, where they are approaching, whether that is why I'm asking these kind of questions.
Yeah, I understand. Yeah, I mean, not only for this new technology, even for the old technology also we have, what you can say, like the infrastructure is very poor in the case of in our country, unfortunately. So even if we want to develop some good chips also, we have to resort to some foreign countries. I mean, we need people to do research in this area and engineer these kind of new technology, and so that our country can be self-sufficient. The thing is that actually, if you are going for outside countries, even for simple things, they are charging like very high amount. So I have heard, like in the case of the microwave components, some of these micro devices can be very cheaply developed if you are developing in our country. Cost wise, there will be maybe 150 something like that. But if you're importing, they will be we have cost around $100 something like that. So the problem is the technology transfer. I mean, that what you can say, like the technology should be implemented. We know the theory, but the theoretical, the practical implementation, we are lacking in that domain. So that is there in all, not only in RF technology, but also in this optical as well as all the technologies.
Okay. Yeah, we in 2012 itself, myself and Dr. Prabhu are already involved in that proposal development in the FSO transceiver design.
Good, sir. Yes, sir.
So due to that fabrication difficulties only they are developing some chips based upon the recent technology. So that we are not getting any project related to the FSO. FSO also recent technology. The people may also
yes. Yeah, correct.
Interested to register PhDs in this field also. So it is current developing field.
Yeah, yes. A very new area.
Yeah.
Those who want to pursue, they can always pursue. A lot of scope is there, but basically almost work are going in the theoretical domain. That's what I mentioned in the future scope. There is a scope for the practical implementation, but due to many reasons that is limited, unfortunately.
Yeah. You already analyzed a lot of things in FSO. Why can't you approach with other IITs? You make it your own hub to develop your own project and try to get the project from Government of India and develop in the real-time chips. So I think Government of India won't give the fund to crores of rupees to one single institution. This kind of project, this is the recent technologies. So better to approach any IITs who really interested to involve in this kind of recent technologies. Then probably submit the one proposal combined with IITs or any research lab like ISRO and DRDO labs. Then you probably get the proposal and enjoy with this development of transceiver.
Yes. Yes, you mentioned there is a welcome suggestion. So we'll always looking forward to collaboration and projects. So as of now, actually, I'm rather a new, recently joined faculty. So I'm just working with project proposals and all. So surely I will try to incorporate these things.
Okay. Yeah.
Thank you for the
suggestion. It's very informative and useful. Very nice presentation. Thank you, Dr.
Yeah. Thank you so much. Thank you so much.
Thank you so much, sir.
Yeah. Thank you.
I once again thank Dr. Vinit, sir, for giving us in detail about history of optical wireless communications, FSO systems and their features, and also their performance analysis, and how we are using FSO communication with spatial diversity, that is using spatial diversity, and many more, which are very useful for us, our participants in the stream of wireless communication networks, that is those who are choosing for the research area. Thank you so much, sir. Also, we look forward for many more sessions in future for us like these sessions. Thank you so much.